Good evening, students, and welcome to today's session. So let's get started. So we will continue again with heat and thermodynamics, first law of thermodynamics applications that we were looking at in the last lecture. We will continue from that today. We will discuss the major test 7 test paper in the next lecture. Just give some time to everybody to go through the paper and try out all the questions once more. In the meantime, today we shall continue ahead with the applications of first law of thermodynamics. So the statement of first law being that the net heat supplied in a thermodynamic process is equal to the change in internal energy plus work done by the gas. So far we had seen three of the standard processes. We had seen isobaric process, which is constant volume. So what happens in this is that pressure becomes proportional to temperature because volume is constant, and the heat capacity is equal to CV. So Q is equal to NCV delta T. Change in internal energy is equal to NF by 2R delta T. And work done by the gas is zero because it's constant volume. And as far as the graph is concerned, we had seen that the PV graph looks like this. Looks like a vertical straight line. So depending on whether we are going from a lower pressure to a higher pressure, the temperature would be increasing or decreasing. So if at a constant volume, go from pressure P1 to pressure P2. This kind of process, whereas if you come in the opposite direction, then the pressure would be decreasing as the temperature would be decreasing. So this was the first of the four named processes that we saw last time. So from this, we also saw that the important relation that CV, that is isochoric molar specific heat capacity of an ideal gas, is given by the formula F by 2R, where F is the degrees of freedom. So CV is equal to 3 by 2R for monoatomic gas, and it's equal to 5 by 2R for diatomic gases. This was also two important special formulae that we saw from the application of first law of thermodynamics to isochoric process. Okay, then the second process we saw was isobaric. So that was one where the pressure is constant. So this is one where volume is proportional to temperature. The molar specific heat capacity is Cp. So Q becomes NCP delta T. Delta U is F by 2R delta T. So remember that delta U is a state function. So it is same for all processes. So whether it is isochoric, isobaric, or any other type of process, the formula for delta U will be the same always. Okay, and work done becomes P delta V because pressure is constant. So that is the same thing as NR delta T. And this is our pressure versus volume graph. Then an isobaric process in this, as you know, will look like a horizontal line where the pressure is constant. So we are going at some constant pressure. This, you can see that E to B here would be an isobaric expansion. And B to A, on the other hand, would be an isobaric compression. You can see that temperature at B is greater than temperature at E. So in the event of our isobaric expansion, the work done by the gas would be plus of P naught into Vp minus Va, or Nr Tv minus T. Whereas in the case of this, the work done would be P naught into Va minus Vb, which would be a negative quantity. It would be negative of area, whereas this is positive of area, this area. Okay. So this was the description of the isobaric process. So now here, further from the application of first law of thermodynamics, you would also see that you get the relation that NCP delta T is equal to NF by 2R delta T plus NR delta T. Because this is our Q, this is our delta U, this is our W. So we get the relation that Cp is equal to F by 2R plus R. So this becomes another important formula. And of course, comparing it with the earlier formula, we have a relation that Cp is equal to Cv plus R. So not equal to, but Cv plus R. So this is another important formula. So Cp is equal to 5 by 2R for monoatomic gases, 3 by 2R for diatomic gas. Okay, then finally the third process that we had seen in the previous lecture was the case of the isothermal process. Yeah, Cp for diatomic gas is 7/2. Sorry, please make a correction here. This is not 3/2. This should be 7/2 R. That's correct, Varun. So Varun has pointed out this. Please make sure all of you made this correction if you noted this down. This should be 7/2 R because Cp is equal to Cv plus R. So for in the above example, you can see that Cv itself for diatomic gas is 5/2. So Cp should become 5/2 plus 1 into R. So that's 7/2 R. So make the correction in this value, please. Okay, now moving on to isothermal process. All right. This is also something we'd seen in the last lecture. In isothermal process, the temperature is constant. Remember, in thermodynamics, when we talk about temperature, generally we are referring to absolute temperature. So anytime you're substituting the value of capital T in a formula, you'd always substitute it in kelvins. Yeah, we will be solving, don't worry. Let us finish the applications of first law of thermodynamics first today. Then we will solve some questions from H.C. Verma. Yeah, so coming back to this isothermal process, the temperature is constant. So what happens as a result of that is that delta U becomes 0 because change in temperature is 0. Delta U in general is defined as NF by 2R delta T. And for isothermal process here, delta T is 0 because temperature is constant. So that being the case, we can see that Q is equal to W, which is equal to integration PdV. Okay. Now the other thing is, because temperature is constant, also P is inversely proportional to V because P is equal to nRT by V and T is constant. So first of all, the graph of pressure versus volume is a hyperbolic graph. When the temperature is constant, the graph will tend to have a shape like this. And during the process, if at any general point the pressure and volume are related like this, then because temperature is constant, so P1 V1 is equal to P2 V2 is equal to P into V at any point. This is called an isotherm. This curve is called an isotherm. Pressure is inversely proportional to volume. So it's a hyperbolic curve. An isotherm is an example of an hyperbolic curve on the PV space. Okay. So for any point on the isotherm, this relation holds true. Okay. So that's the first thing. Now also, you would see here that A to B in this graph, A to B would represent an isothermal expansion, whereas B to A would represent an isothermal compression. because you can see that P1 is greater than P2, which implies that V1 is less than V2 because temperature is constant. Okay, so now when it comes to calculating the work done, we have to substitute this condition that pressure is inversely proportional to volume in this. So the heat supplied, which is equal to the work done, becomes nRT, or let's put it this way first, that integration of pressure with respect to volume. So that is nRT by V to dV integrated from whatever initial to final point. So because temperature is constant, we had seen it becomes a logarithmic expression. So finally, we get Q is equal to W is equal to nRT, which is a constant, into natural log of final volume divided by initial volume. So in this graph, you can see that if we are going from A to B, Q will be equal to W will be equal to nRT natural log of V2 by V1, which would be a positive quantity because V2 is greater than V1. Whereas if we went from B to A, which is a compression, okay, this would be V1 by V2, and this would be a negative quantity because V1 is less than V2. Okay. So B to A is an isothermal compression. So Q is negative, W is negative, whereas A to B is an isothermal expansion. So Q is positive, W is positive, which means heat is supplied to the gas and work is done by the gas. While the temperature is constant. Okay, whereas this case, heat is absorbed from the gas and in this case work is done on the gas, because work done by the gas is negative. That means work is being done by the external agent on the gas. We'd also looked at the visualization of these processes with respect to the experimental method. So in the case of isothermal process, remember what is happening is that the piston is free, but the temperature of the gas remains constant while we are supplying heat to it or withdrawing heat from it. Yes, that is correct, Samar. The straight lines which represent the isobaric process, which is a horizontal straight line, they are called isobars. And the vertical straight line which represent the isochoric process, they are called isocores. So the names given to the horizontal line and the vertical line on the PV graphs are isobars and isocores because they represent isobaric process and isochoric process. That's correct. Okay, now a couple of important things to further note down about isochoric process. Sorry, isothermal process. In an isothermal process, molar specific heat capacity C is undefined. Okay, because Q is non-zero, whereas delta T is zero. So C, which is Q upon N delta T, this becomes undefined. So that is why you never hear the term isothermal specific heat capacity. You will hear isobaric and isochoric specific heat capacity, which are Cp and Cv. But for isothermal process, we cannot define heat capacity because we are supplying heat, but that heat is getting converted to work, or we are absorbing heat at the cost of work done on the gas, but there is no temperature change. So heat supplied per mole per degree change in temperature cannot be defined because temperature is not changing. So that's one important point. Secondly, as we saw that the way to perform an isothermal process would be if the gas is kept in a container with a free piston, the piston can move freely, and with conducting walls. Okay. So if load is slowly added to the piston, that is, the mass is increased, this mass M is increased, then there is isothermal compression. So we increase the mass, work is done on the gas, and heat comes out of the gas. Whereas if we gradually remove mass, from the same situation, we very slowly remove the mass. Now we make it M minus delta M. So the gas does positive work because the piston is pushed up and heat comes into the gas. Okay, so this is how we would practically achieve isothermal expansion or isothermal compression in a laboratory kind of method. We'd have to fix up some kind of arrangement like this so that the temperature of the gas is remaining constant while we are slowly making it undergo an expansion or compression. So I'll just minimize this so you can note down both these points. Okay, next up, let's look at an example question. So a sample of nitrogen gas initially at a pressure of 1 atmosphere, volume of 2 liters, and temperature of 200 kelvins. Yeah, I'll take you back, Viraj. Let's write down this question first. Is first heated at constant volume to a temperature of 300 kelvins. And then expanded isothermally to a volume of 4 liters. Okay. And finally, compressed back to its original, oh sorry, not 4 liters, okay, to volume V3. And then it is compressed back to the original volume. Of this. Okay. But isobarically. So first of all, draw PV graph and show each of the 3 processes in the same graph. Okay. Secondly, express the state of the gas at the end of first process. Okay, so just try out this question. Viraj, I'll take you back to the note earlier, but just use the formula and the concepts that we've discussed for all the three types of processes: isothermal, adiabatic, and isothermal, isobaric, and isochoric that we've discussed just now. So both the conceptual part as well as the formula will be applicable in this question for each of the three. So just try it out. Okay, very good, Dhruv. That's correct. The second point that we found is correct. Now you have to just continue in that regard and see what to do about the third and the third point at the end of this second process. So the best way to do this type of problem, and actually in general many problems in heat and thermodynamics, which are based on these standard processes, the named processes. The best way to approach them is to first visualize them on the PV space. It just makes things easier, which is why I've emphasized on the graphs for the three processes we've studied till now. So we saw that we are going from a state of P1, V1, T1 via an isocoric heating process, because we're increasing the temperature to T2, which is 300 Kelvin. Okay. So that P1 was 1 atmosphere, volume was 2 liters, and temperature was 200 Kelvin. So that kind of process looks like a vertical straight line. So immediately we know that on the graph, our first process is going to be a vertical straight line in which you can see that temperature is increasing. So it must be going vertically upwards. The temperature T1 at this point is 200 Kelvin. Temperature at this point is greater, so it has to be vertically upwards. Okay, which also means that the volume is 2 liters because it's isocoric. Okay, but what about the pressure? So during an isocoric process, pressure is proportional to temperature. So P2 by P1 should be equal to T2 by T1. So using this relation, I'll be able to work out that the pressure will become, the temperature is 3 by 2 times the initial value. So the pressure will become 3 by 2 atmospheres or 1.5 atmospheres. So I can also see that if I relate the pressure in atmospheres, the volume in liters, you also see that this common volume V2 is equal to V1 is 2 liters, but the pressure is increasing from its initial value of 1 atmosphere to a final value of 1.5 atmosphere. Okay. I'm not drawing the graph to scale, don't need to worry about that. Okay. Now the next thing we are doing from this state, next thing we are doing is we are going through an isothermal process. Okay. To some final pressure, final volume, and final temperature. Now the only thing is we know the temperature will be constant because it's isothermal. So because it's isothermal, the temperature T3 will be equal to the temperature T2, which is 300 Kelvin. Okay. So now what we'll do is instead of drawing the whole isothermal process, we will just draw an isotherm and we'll see what we can predict about the direction in which we are going in the isotherm. So we'll just draw a hyperbolic graph which represents an isotherm passing through this point. So this is the isotherm at a temperature at 300 Kelvin. Okay. Now where I'm reaching, that I will also get a clue from the fourth process. I mean from the third process. Next after this, what I'm doing, I'm going through an isobaric process back to a pressure which I don't know. Okay. But a volume which I know is back to the original volume of 2 liters. Okay. Now because this isobaric, okay, and it's coming back to the initial state. Okay. So that means what is happening? I must be going like this because the question is saying that I'm coming back to the initial state. The fourth process must be like this. I mean, the third process must be like this. It's an isobaric compression. So that means my isothermal process must have been from here to exactly to this point, so that I can come back to my initial state isobarically. Okay. Now you can see that because of this, okay, this volume, or rather this pressure, P3 has to be equal to P1. So it is 1 atmosphere. So therefore, P3 V3 is equal to P2 V2. So from that we know that V3 is equal to 1.5 times V2. So 3 liters. Okay. So that's how we know that this must be 3 liters. Only then we can come back isobarically to our original state. So it is like we have to do a bit of trick over here. We have to do back calculation. To the right, we understand that it's an expansion, but the question is up to where it's expanding. Is it going beyond this point, before this point? So that we understand from the nature of the third process, that the third process is an isobaric process, bringing it back to original state. Okay. Compress back to its original volume. Actually, we'll write this as original state. Not just volume, but original state. That is P1, V1, T1. It's coming back to that original state. So if it's coming back to the original state here, the point 1, then that means the point 3 must be having the same pressure as the point 1. So that becomes the point. That becomes the main point over here to catch that this thing. Because you're coming back isobarically to the same original state P1, V1, T1. So P3 must be equal to P1. So once we know P3, we know V3 because the points 2 and 3 are connected by isotherm. Okay. So state 1 to 2 is connected by an iso core. Okay, then 2 to 3 is connected by an isotherm. Okay. And then 3 to 1 is again connected by an isobar. So during an isobar, pressure is proportional to temperature. During isotherm, what is happening? Pressure is inversely proportional to volume. And during an isobar, volume is proportional to temperature. So this is what we are. So this is the second. So we have found out the states. Okay, so P1, V1, T1. The initial state was 1 atmosphere, 2 liters, 200 kelvins. From there we went isochorically. So the pressure increased to 1.5 atmospheres, but the volume remained the same. Temperature increased to 300 Kelvin. From there we went isothermally to this point where the pressure reduced to 1 atmosphere. So the volume increased to 3 liters while the temperature remained 300 Kelvin. And then from there we went back here by an isobar. And from here to here by an isobaric process. Then from here to here by an isothermal process. And then back by an isobar. Okay, so this question is a little bit technical. You have to be sure that you understand the graphs of each of these so that you can connect the unknown quantities. Or you can connect the processes by the graph and understand the unknown quantities. Okay, next up, we'll understand this thing, the values of Q, delta U, etc. Okay, so let's come to the last part. So now Q delta U W for each process. Now the gas was nitrogen gas. So the degrees of freedom would be 5, diatomic gas. Now we can write it like this, that nRT2 is P2V2, nRT1 is P1V1. Now in this V1 was equal to V2 is equal to 2 liters. So that is 2 into 10 raised power minus 3 meter cube. P1 was 1 atmosphere. So that's 10 raised power 5 meter, sorry, 10 raised power 5 pascals. Whereas P2 was 1.5 atmospheres. So 1.5 into 10 raised power 5 pascals. So this quantity Q equal to delta U will be equal to write this like this only. Okay. So 5 by 2 into 1.5 minus 1 into 10 raised power 5 into the common value of volume, which is 2 liters. That's this much. Okay. And this is in joules now. So 5 by 2 into 0.5 into 2 into 10 raised power 2. So that's 2.5 into 100. So 250 joules plus 250 joules is equal to Q, or that's the same thing as delta U for the first process, whereas W is 0. Okay, now just like we've done for this part, we have to also calculate for the isothermal expansion and the isobaric compression, the values of Q, delta U, and W. Okay, anybody got the values for the second and third process? So the second process was the isothermal expansion, okay, going from P2 V2 T2 to P3 V3, obviously T3 equal to T2. So this is going from a pressure of 1.5 atmospheres and a volume of 2 liters at a temperature of 300 Kelvin to a final pressure which was reduced back to 1 atmosphere, volume that expanded to 3 liters. So in isothermal expansion, work done is zero. Sorry, delta U is zero, change in internal energy, because change in temperature is zero. So, but Q is equal to W is equal to nRT, natural log of final volume upon initial volume. So this is nR into 300 into natural log of V3 by V2. So Q will be equal to, now see, P2 V2 is equal to nR T2. So is equal to nR into 300. So we can substitute nR into 300 as 1.5 into 10 raised power 5 multiplied with, in SI unit, that is. So this much in joules. So 300 joules. Yes, that's correct. Very good, Shekhar. You can substitute this here. And V3 was equal to 3 liters. V2 is equal to 2 liters. The value of nR into 300 will be 300 joules, but then we have to multiply it with that log factor. So 300 joules multiplied with ln of 3 by 2. So 300 ln 3 by 2 is, okay. Now ln 3 by 2 also we can do a rough calculation. 2.303 log 3 by 2. Okay. So approximately 2.303 log 3 is about 0.48. Log 2 is about 0.30. Okay, Viraj, I will check that answer out. Whereas delta U is 0. So this is what we are getting for the isothermal expansion. Okay. Now we will do the same kind of process, same kind of calculation, but for the third process, which is the isobaric compression. So make sure the calculations are clear, people. Yes, Viraj, that's correct. Isobaric process, the W will be equal to minus 100 joules, and the Q will be minus 350 joules, whereas delta U will be minus 250 joules. So if you're getting that, then that's correct. Okay, so let's quickly finish the last part, the isobaric expansion part. Sorry, the isobaric compression, not expansion. So that went from initial state P3, V3, T3 via isobaric back to P1, V1, T1. So P1 is equal to P3 equal to 1 atmosphere. But the volume compressed from 3 liters back to 2 liters. And as a result, the temperature went down from 300 Kelvin to a temperature back of 200 Kelvin. Okay. So delta U is Nf by 2R delta T. So that is N into 5 by 2R into T1 minus T3. So this is the initial state and this is the final state. So final minus initial. So it is 5 by 2 into nRT1 minus nRT2. So nRT3. So we can write this as 5 by 2 P1 V1 minus P3 V3. But P1 is equal to P3 is equal to P, suppose. So this is the easiest way of doing this calculation. So 1 atmosphere into 2 minus 3 liters. So that's minus 250 joules. This is our delta U. Now from this you can see it's very easy. Yeah, I'll show you the last one. Okay. That W is P delta V. So it will just become 1 atmosphere into 2 minus 3 liters, or become minus 100 joules. And once you got this, now Q, we can either do NCP delta T, so N into 7 by 2 R, T1 minus T3, or we can simply say, okay, that Q is delta U plus W, because you've calculated two of these already. So Q is equal to minus 350 joules. So we don't need to separately do a calculation also. So these are the three values for our isobaric compression. So this is the thing you have to get used to in this chapter. Okay, these are the most common type of questions from this entire section of heat and thermodynamics in JEE. The maximum percentage of questions is going to be from application of first law of thermodynamics, where it's this sort of analysis that you have to learn to do. Okay. Where to apply what formula and how to visualize from the graphs, and always use a combination of the first law of thermodynamics statement and the equation of state, PV equal to nRT, and the basics like degrees of freedom, the value Cp, Cv, etc. So these are all the things you have to keep in mind. Once you get used to using these parameters and visualizing the process in the graph, etc., you see that in general there's a much easier chapter. There's a much easier section of physics compared to mechanics. Lot less chances of making mistakes or getting stuck in questions. But you have to be clear on the concepts from the beginning. So make sure that you are spending a lot of time in redoing the derivations that I've done in class and understanding each and every step. Don't try to do a formula memorizing type of approach. Don't try to memorize the formula. Try to make sure you understand the derivation so that you naturally remember the formula. You don't have to memorize them. Okay, so these were about 3 of the 4 standard processes. Now we come to the last and final one of the standard processes, which is called the adiabatic process, as you probably know from chemistry. So an adiabatic process is one where there is no heat exchange. Adiabatic process is one where there is zero heat exchange of the gas with respect to its surroundings during the process. So the experimental way of conducting, or the experimental way of visualizing an adiabatic process would be something like this. We use the piston only to compress or expand the gas. Okay. But the container this time is isothermal in nature, which means that it is having non-conducting walls or insulating walls. So we have a container with perfectly insulating walls. and a movable piston on which we can add some load or subtract load in order to expand or contract the gas. Okay. But difference is, unlike the isothermal process we had done earlier, this time the walls of the container are what we call adiabatic walls. That is, they are non-conducting walls. So there is no heat exchange with the surrounding. So these are insulating walls or non-conducting. By non-conducting, we mean non-conducting for heat. Okay. This is a free, but at the same time insulated piston. It's free to move, but it does not exchange heat. Okay. So if we add mass by adding mass slowly, we can make the gas undergo an adiabatic compression. So what you'll see in that is that work is done on the gas. Okay. And its internal energy increases, but there is no heat exchange. Okay. So work is done on the gas means work done by the gas is negative. Okay. Internal energy increases, but Q is 0. So by first law, you can see that for an for an adiabatic compression, what would happen in an adiabatic compression is that Q would be 0, delta U would be positive, and W would be negative. Whereas if we remove mass and allow the gas to expand, then the opposite would happen. As the gas expands, it would do positive work, so W would be positive, but it would lose internal energy, so delta U would be negative. So first just note down this thing, then we'll discuss about the opposite of this, where we remove mass slowly. So we allow the gas to expand by pushing the piston, and in the process lose internal energy because there's no heat exchange. Yeah, there was some disturbance at my end because of work going on. So anyway, so now there will be no further work or drill machine. So anyway, now let's understand the reverse of this. On the other hand, if mass is slowly removed from the load on the piston, okay, this load over here, from this, if we are slowly removing the mass, then what is going to happen is that the gas expands adiabatically. So in this case, what is happening is that in an adiabatic expansion, work is done by the gas on the piston. So that means by a sign convention, W is positive and its temperature or internal energy drops. It loses internal energy. So delta U becomes negative. Okay. And Q is zero, of course. So in this equation only, you can see that Q remains zero, but delta U is this time negative and W is positive when the gas undergoes an adiabatic expansion. Whereas in a compression is the opposite of that. And this is how we would execute the expansion or compression at an experimental or laboratory physics type of level. Okay. So next up, we'll see the equations involved, but this is the conceptual part. Now, one thing you'll notice which is different about adiabatic process is putting the condition Q equal to 0 does not give us anything specific in the ideal gas equation, PV equal to nRT. If we put Q equal to 0, neither we get pressure is constant, nor volume is constant, nor temperature is constant. So just the fact that Q is 0 does not give us any equation between pressure and volume. We have to generate the equation using first law of thermodynamics. So that's the next thing we will see. W is positive and its temperature or internal energy drops. Okay, work is done by the gas and its temperature or internal energy, because temperature is proportional to internal energy. Remember, U is Nf by 2RT. So the temperature drops, which means that the internal energy decreases. So delta U is negative. Okay, so hope that is clear, Samar. Okay, now next thing, let's understand the application of first law for adiabatic process. Okay. So Q is equal to 0. So that also means that molar specific heat capacity is 0 for adiabatic process. Molar specific heat capacity. Okay, I'll go back, Durga, just a second. 0 for an adiabatic process. because remember C is equal to Q upon N delta T. Now there is no heat exchange, Q only is 0. So that means molar specific heat capacity is 0. So the process is such that there is no heat exchange. So the heat supplied per degree change in temperature is 0 because no heat is supplied. At the same time, temperature changes because of exchange of mechanical work. So when work is done on the gas, its temperature increases. When work is done by the gas, its temperature decreases. Okay, very good. So now moving on further, you can see that now Q is equal to 0. That means that delta U plus W is equal to 0. So work done is equal to minus of delta U. Okay. Now delta U is a state function, so it will always come from the standard formula that it is NF by 2R delta T. So therefore W becomes minus of NF by 2R delta T. So Q is 0, delta U is the standard state function, and W becomes minus of work done. So these are the three formulae for Q, delta U, and W. The three terms of the first law of thermodynamics in this. Okay. Now next thing, to determine the PV graph or curve in an adiabatic process. So one is we will make use of equation of state PV equal to nRT. When we write this in differential form, we have PdV plus VdP is equal to nRdt. We are just using the fact that P, V, and T all three are variable. So when you use product rule, so into derivative of PV R and R into dt. dt. Yeah, students, so there is a little bit of connectivity issue at my end. Okay. So now eliminating dt between equation 1 and 2. So from here you can see nr dt. This term is minus f by 2 into nr dt. So this nr dt can be substituted from here, from this equation onto this. And this becomes pdv plus vdv. So you can see that we get 1 plus f by 2 pdv is equal to minus of f by 2 vd, or dv by v into 1 plus f by 2 upon f by 2 is equal to minus dp by 2. Say like this. Now you can see that cp is equal to 1 plus f by 2r and cv is equal to f by 2r. Therefore, cp by cv is 1 plus f by 2 upon f by 2, or 1 plus 2 by f. So this term is given a special name called gamma, called the adiabatic constant. Given by the formula Cp by Cv, or that's the same thing as 1 plus 2 by. Okay, so you can see here 1 plus 2 by f dv by v is equal to minus dp by, or gamma into dv by v is equal to minus dp by v. So this is what we are getting from equation 1 and 2 after eliminating the temperature. Now when we integrate this, we will get the standard equation of adiabatic curve, which you might have seen in chemistry, that it is this thing, we call it PV to the power gamma is constant. Okay, so I'll just minimize this a little so you can follow the steps, how we have reached up to this point. Okay, so next step we have to integrate this. Well, let's say initially the pressure was P naught when the volume was V naught, and at some time T the volume is V and the pressure is P. So we have minus of ln P from P naught to P is equal to gamma times ln V from V naught to V. So minus ln P by P naught is equal to gamma times ln V by V. Now we can take the powers inside. So natural log of P by P naught to the power minus 1 is equal to natural log of V by V naught to the power gamma. So we have P naught by P is equal to V by V naught to the power gamma, or P naught V naught to the power gamma is equal to PV to the power gamma, or in general we can say that PV to the power gamma is constant, or pressure, that's not alpha, that's gamma. So the pressure is inversely proportional to 1 upon V to the power adiabatic constant gamma. This is the equation of an adiabat, that is the graph of an adiabatic process. Now, of course, keep in mind here that gamma is Cp by Cv, or 1 plus 2 by F. So gamma has a value of 5 by 3 for monoatomic gas, and gamma has a value of 7 by 5 for diatomic gas. And the graph of pressure versus volume. That will also be a hyperbolic curve, but its shape will be slightly different compared to isotherm. This is an adiabatic expansion from some volume V1 to V2, pressure P1 to pressure P2. So P1 V1 to the power gamma is P2 V2 to the power gamma. Now in comparison to this, if you look at an isotherm, the isotherm would be looking like something like this. This is an isotherm. This drops more sharply, the adiabat, because gamma is greater than 1. So that's why. See that gamma is greater than 1 always, because it's 1 plus 2 by F. Okay. So that is all the information required about adiabatic processes. And with that, we finish the applications of first law for all the standard type of process. Okay. So I will send you an additional list of questions from H.C. Verma. And next lecture, we will keep for discussion of questions, both from kinetic theory of gases as well as from first law of thermodynamics chapter. And if there's anything pending from thermal expansion, etc., we'll discuss those questions also. Okay. So next couple of lectures will be discussion lectures, because we have to discuss the MT7 paper also, as well as the question set from H.C. Verma. Okay. So that's it for today's session, people. Wish you all the best.